So, right, nice to be here. That's only the title of the first talk. The second one is going to be connecting some of this framework with, or maybe zooming in on part of this framework and talking about line operators and braided tensor categories and vertex algebras in the same sort of context that vortices are also appearing in. This talk, I guess I also need to look down. This talk is also meant to be an overview of sort of the sorts of things that exist in these 3D n equals 4 theories, maybe summarizing some of the things that happened last week, and prefacing a few of the other talks from this week. My starting point here is in physics. And in physics, I would say that we are investigating properties of 3D n equals 4 theories. They come in several different flavors. They're the ones I'll discuss here and that are under a lot of current study are gauge theories with linear matter, meaning they're labeled by a compact group and a linear quaternionic representation thereof. And I'll always assume for things I'll say that the representation is of the form T star V, where V is a unitary representation. And for a lot of the algebraic statements, it's also useful to complexify the group. So G is going to be the complexified reductive group. But there are also 3D n equals 4 theories labeled by nonlinear targets, by smooth hyperkähler manifolds. And there are other various modifications, Simon Z theories that show up that I won't discuss. So I'm calling the theories either TGV or TY, depending on what sort of data they're labeled by. And each of them admit two different topological twists called A and B. The A twist is, just to connect a bit to the past, the A twist is a dimensional reduction of Witten's Donaldson twist. The B twist was discussed by Blau and Thompson, and in the case of smooth hyperkähler targets, is the thing that Rosansky and Witten used to define their invariance. I will mainly focus on the A twist today. One expects in either twist to get a fully extended 3D TQFT, or rather fully extended down, maybe well-defined on 3 manifolds. So this is why I call them a 3210 with 3 in parentheses. The value on 3 manifolds may or may not be defined. But optimistically, get a 3D TQFT out of either twist. There are more little caveats that I'll just say quickly. So they depend on either a spin or spin C structure on an underlying 3 manifold. As I said, they may not be defined on unclosed 3 manifolds due to some infinity going on, and state spaces on surfaces are almost always infinite dimensional. Moreover, they're of cohomological type, and I just mean that all of the spaces, categories, etc., that are showing up are DG objects up to quasi-isomorphism. And finally, some things may break in the case of smooth hyperkähler targets that are perfectly fine in the gauge theory setting. In particular, there may be things like framing anomalies or reductions of grading showing up in the hyperkähler case that not going to be a big part of this talk. The caveats about infinite dimensionality of state spaces and invariance not being defined in the top dimension are not new here. These are familiar features in two-dimensional A and B models. Example, taking the 2D A model with target C star, one, I guess, physically would say that the space of local operators looks like functions of X and X inverse. Mathematically, you'd say symplectic cohomology of C star is functions of X and X inverse, which is infinite dimensional. And that makes the two torus partition function ill-defined. So similar things happen in 3D. However, as one gets lower in dimension, things are better and better behaved. Also, so I mentioned these two different twists. In 2 dimensions, one has mirror symmetry that relates A and B twists with different targets. And in 3 dimensions, there's an analogous physical duality called 3D mirror symmetry that relates some pairs of gauge theory data, GV and G dual and V dual, or in some cases relates a gauge theory to a smooth target Y, or in many other cases, we just, well, I'm going to say we just don't know. In fact, in many other cases, you can show that there's neither a gauge theory nor a hyperkähler dual. I guess physically we talk about non-Lagrangian theories that are mirror to Lagrangian ones, which is to say 3D mirror symmetry works beautifully in some infinite families of examples and data, but is not, well, yeah, is not something you can quite apply to every theory. They're nice pairs. I would say it's actually the same in 2 dimensions. It's just that we haven't really, people haven't talked about the really nasty examples in 2 dimensions because Calabi-Yau hypersurfaces in toric varieties are all nice. 3D mirror symmetry swaps A and B twists and relates things that are computed in an ATQFT to things that are computed in a BTQFT and vice versa. That leads to a lot of rich dualities that are currently being explored in geometry and representation theory. It also, often the B side is something that's easier to access, and then mirror symmetry sort of tells us how to develop or define or find things about the A side. So very briefly, I threw TQFT up here. So what is a TQFT? The fancy definition involves some functor from, here in 3 dimensions, a 3 cobordism category to some higher DG 3 category. Practically, it's a functor from 0, 1, 2, and 3 manifolds, possibly with boundaries and corners of various kinds, to linear algebraic objects. At the bottom level, this functor sends a point to some 2 category. Physically, we call that a 2 category of boundary conditions. And it's the analog of like the Fukaya category in the 2D A model. So this 2 category is expected to be like a 2 categorification of Fukaya categories. And yes, does a lot of other things. Sends a circle to a braided tensor category of lines that I'll discuss in the next talk, where having a tensor product on lines, you have a pointer, having a tensor product on lines comes from a disk with two little disks removed as a cobordism. Having a braiding comes from a three-dimensional cobordism that moves circles around within a disk. More of what I'll discuss today in some brief examples is what happens at the higher levels. So to a closed surface, one expects to get a vector space. The vector space assigned to a two-sphere is special because it has a canonical product on it, and the product comes from a 3D pair of pants, or a ball with two little balls removed. And the fact that there's no higher dimension around, and you can move little balls inside a big ball for free, it tells you that this product is commutative. And if you're a bit more clever about it and notice that everything is living in the DG world, it's not just commutative, but it's an E3 algebra of local operators. I'll say about that now. And finally, right, for closed three manifolds, we usually expect to get numbers. Those numbers might be infinity or zero. One way, sort of useful way to regularize what happens at the top dimension, which is something that is done mathematically in other QFTs as well, is to remove balls and not evaluate on a closed three manifold, but on the three manifold with the little ball removed. That tends to be better behaved. So again, much of this, like sort of defining the things on the right-hand side of this slide, in the case of gauge theories, and in the A-twist of hyperkähler targets, is active work in progress for most of this. A lot of this active work in progress takes inspiration from work of Kapustin-Rózanski and Salina on Rózanski-Witten theory, on the B-twist of hyperkähler targets. So they actually described all this categorical data in the case that the target is a smooth, complex cotangent bundle. Right. So that's the TQFT part of this. And now you may ask, where are the vortices? And the short answer is that the vortices are sitting in the A-twist. Why are they sitting in the A-twist, and how can we see part of that? The fields of the A-twisted theory on a three-manifold M, there are various ways to try to access like what these TQFTs are, and one of them is to start with fields that you would throw in a path integral and try to quantize that somehow. And so I'm going to focus on that perspective, but there are other ways to try to look at this. One motivation. The fields of gauge theory in the A-twist involve a discrete choice of principal G bundle on the three manifold, a connection on that bundle, and then I guess in physics or in a hyperkähler setting, one would sometimes say a triplet of adjoint scalars. In the A-twist, they go in different directions. So there's a real scalar or a real section of the adjoint bundle, and a complex one. The real one plays a more important role, and the complex one doesn't. That's sort of the data canonically associated to the group G, and then there's data associated to the matter. This is also building on what Nick discussed on Friday. So for the matter, you have to choose a spin bundle, and then a section of the spin bundle tensored with the representation V. And so reminder, the full symplectic representation, or quaternionic rep, was T star V. And the section of the spin bundle, which is two-dimensional, involves some section of V and some section of V dual that's been complex conjugated. And so they sit nicely in a spinner valued in V. Before I say what the equations of motion are, I should also note that when you have this sort of structure of a symplectic representation that's been half conjugated and thrown into a spinner, and you compute the hyperkähler moment maps for the compact group acting on this quaternionic representation, you find that the three moment maps actually belong in a one form. They sort of, because the moment maps are bilinear in the coordinates x and y, the coordinates are sections of a spin bundle. Maybe it's not surprising that when you take bilinears, you'll get something that looks like a one form. And then I can write down the equations of motion. And the important ones, or the ones most useful for building some intuition, are these two here. This spinner of matter fields satisfies a covariant Dirac equation, and the Hodge star of the curvature of the gauge connection is this moment map one form plus the exterior derivative of the real scalar sigma. These are maybe familiar to a lot of you. The abelian version of these, when the vector space V is just C, is known as Seiberg-Witten equations. So these are a generalization of Seiberg-Witten equations to general G and V. The fact that Seiberg-Witten equations are showing up is consistent with what I said at the beginning, that the A twist is a reduction of the 4D Donaldson twist. They have several interesting specializations. One very simple one, if we happen to just kill the matter, kill the spinner, then the equations just look like monopole equations in 3 dimensions. Another specialization that is quite useful is asking for time-independent solutions. Requiring time independence in a 3D Dirac equation just leads to holomorphic equations on a 2-dimensional slice. So sorry, for all of this to make sense, if when I say time independence, if you choose the 3 manifold to be a complex surface times time, and you ask for time independent solutions, then you get holomorphic equations along the surface. And the sigma part, the monopole part of the second equation drops out, and it just turns into a vortex equation that, that I don't need to explain to this audience. Moreover, there's a final equation that I didn't, so time independence plus this third equation, one component of that equation is a vortex equation, and the other components tell you that the complex moment map vanishes. So these are sometimes called symplectic vortex equations. A sketch of what I'm thinking of when I see the 3-dimensional equations is the following. Locally, on this 3 manifold, I can choose a complex space real-time splitting, and I'll expect to get vortices that move along time, whatever direction I've decided to choose as time. That direction on some global three manifold may change. And so they don't all have to be moving in the same direction. And the vortices, in some limit that the vortices are like small and concentrated along lines, the vortices can also change. Basically, I would say they get created and annihilated. And they can be created and annihilated by smooth monopoles, which are sort of the solutions to that equation. And so one can imagine a vortex configuration where at some point, some of the matter fields vanish, the x's become 0, and a smooth monopole interpolates between having a vortex and not having a vortex. That's sort of the 3D dynamics. So assigning useful mathematics to the picture on the right-hand side for one of these general GP gauge theories is something that I don't believe has been done, and that would be quite interesting to see. This is classical. So these are the classical equations of motion in the A-twist. The TQFT functor, in principle, is built by well, looking at what sort of manifold with boundaries and corners, et cetera, we want to throw into the TQFT functor, solving the equations of motion on that manifold and quantizing that space of solutions. In the cases I'll discuss in this talk, that quantization involves taking cohomology of a classical moduli space. And in probably going too fast. I often give a board talk, which goes way too slow, skipping over things. So in the second part of the talk, I sort of want to give a sketch of this quantization procedure for sigma a smooth surface. The special case where sigma is S2, which as I mentioned before, should lead to an algebra rather than just a vector space. And in the A-twist, it's the Coulomb branch algebra, the thing that BFN gave a mathematical definition for that really opened up this field of study. And sorry, it's Braverman, Finkelberg, and Nakajima. And then I'll say how these two play together, giving actions of the S2 algebra on the various vector spaces coming from surfaces. I'll give some examples of that. And this action of an algebra on a vector space assigned to a surface is one mathematical manifestation of my sketch of vortices playing with monopoles. So the sort of thing that's happening here is a linearization, quantization of a picture like this with a fixed time direction. And like the Z of S2 is sort of the red explosion. And the Z of sigma is a quantization of a vortex moduli space. I'll try to make that a bit more explicit. Is not something that's been studied so far as I know. I mean, the other one's not. The other one is what I think would happen when you don't have a global holomorphic foliation of your three manifold. For sigma, a smooth, compact Riemann surface, the vector spaces associated to sigma in the A-twist were described in a recent paper by Bullimore, Ferrari, and Kim. So just to sketch what's happening, as I said, quantization in this case ends up looking like taking cohomology. And the thing one expects to take cohomology of is a space of solutions to equations of motion. And here it's equations of motion on sigma times, well, a slightly thickened version of sigma. This is the way the TQFT game always works, QFT game. So it's sigma times like a tiny time interval. These equations are symplectic vortex equations. In a hand-wavy algebraic setting, one could try to describe that moduli space as sections of a certain T star V symplectically quotiented by V bundle on sigma. So roughly it wants to be maps, holomorphic maps or algebraic maps from sigma to this algebraic symplectic stack. But there's a twist by the square root of the canonical bundle that shows up, which is why I'm saying sections. Now, this, if you want, you can treat this as a stack treat the whole mapping space or the whole space of sections as a stack. But to make it a bit nicer, one imposes stability conditions. And physically, there are certain deformations of the 3D theory that correspond to imposing stability conditions. And that leads to something like quasi-maps into a resolved symplectic quotient, or maps into the stack with stability conditions. And this has, the dependence on stability conditions has interesting wall crossing phenomena, which I think Andrea will talk about later today, perhaps. Unless the plan has changed. You also have to worry when I say things like this. I'm sure you all are all worried about what sort of cohomology is at play here, because the space, even the stable one, might still be singular. I'm honestly, I'm not sure there's a perfect physics answer to that. The physics answer is there is a physics answer, but turning it into sensible mathematics is hard. Say that. What ends up, so if one is a mathematician, one doesn't care. One tries to find a sensible cohomology theory and to prove results about it. And so what actually ends up being used is either intersection cohomology. In this case, it's some equivariant intersection cohomology, or Borel-Moore homology. A sort of even, in some ways, simpler version is of the story involves taking the surface to just be C, non-compact. And that's a story I developed with Matt Bullimore, Davide Gaotto, Justin Hilburn, and Heechul Kim, that generalizes a mathematical result that was not initially related to 3D gauge theories or Coulomb branches or anything like that. Had to do with actions of finite W algebras on quasi-maps into flag varieties by Braverman, Fagan, Rubnikov, and Finkelberg. We described this a bit. So to make sense of a space assigned to the complex plane, one needs to do something at infinity to sort of compactify C. One thing to do at infinity is to choose a point in the stable part of the stack and require maps to asymptotically approach that point near infinity. And that effectively ends up compactifying the problem and leading to a moduli space of maps from P1 that are base pointed at infinity, where you fix, so now compact domain, and you just fix what happens at infinity and start looking at quasi-maps sort. And these base pointed quasi-maps are what were studied previously in the case where the target was a flag variety, but this works much more, can be set up much more generally. Oh, sorry. Well, so if I say quasi-maps, it's quasi-maps into a smooth thing. Or I could just say it's maps into the stack with a stability condition, where the stability condition is that you don't hit the unstable locus more than a finite number of times. I was trying to balance notation that might appeal to different people and might have done a poor job mixing it all up in the end. Okay, so one can define this, and the cohomology that goes here in this case, that at least that we used, was intersection cohomology. Presumably Bohr-Elmore would work as well. But so what? Why is it interesting to study cohomology of spaces of quasi-maps or symplectic vortex moduli spaces? And the answer from the 3D TQFT point of view is that all of these spaces naturally get actions of the algebra Z of S2. The action comes from a 3D cobordism involving the surface we're talking about times an interval with a little ball removed. That's a map from the incoming spaces, which are Z of S2 for the ball, and the thing on the bottom, say, to the space on the top. That in principle defines the action. And this ends up connecting these spaces of quasi-maps or cohomology of these spaces to representation theory. So I need to say a little bit about what Z of S2 is. It presumably can be constructed, well, sorry, it certainly can be constructed as a vector space by doing what I just said, replacing sigma with S2. For a problem that has a natural real complex splitting, where the 3 dimensions in my 3 manifold are split into real and complex, in order to get a vector space that has a natural algebra structure, it is more convenient, rather than taking a smooth S2, say something like P1, not base pointed, to consider this non-Hausdorff algebraic space that some of us call the raviolo and others of us call the bubble or the UFO. so this raviolo is an algebraic manifestation of S2. It's formed by taking two formal disks and gluing them over a formal punctured disk. And so the reason this looks like S2 is that if the puncture that you're removing in the gluing were regularized a bit and made finite, this would topologically literally be S2. And this sort of space comes up when one considers Hecke modifications. Right. So then what's the expectation? If I plug this algebraic space into an algebraic manifestation of what this TQFT should spit out on a surface. Well, first, I was saying I expect to get an algebra here, and the algebra that it should be is what physicists call functions on the Coulomb branch. Right. So if one actually tries to work this out, what does one find? Ignoring derived stacky structure, one finds that maps from the raviolo to the symplectic quotient boil down to having sections X and Y, well, of a trivial bundle on the bottom disk, meaning Taylor series valued, elements of V and V dual valued in Taylor series, an isomorphism between the top and the bottom everywhere except at the origin, which is an element of the algebraic loop group, together with the condition that once you get to the top, you can still extend over 0. So acting with G on X and on Y still lands you in Taylor series at the top. There's also this algebraic complex moment map condition that has to be imposed. And then one's quotients by Taylor series isomorphisms on acting on the bottom and acting on the top. So this is what, if one wanted to write down a definition or try to write down a definition for a space of Hecke modifications of symplectic vortices, this would be it. However, I am not sure that anyone has still fully studied an appropriate cohomology theory on this space. And so in Nakajima's first paper on Coulomb branches, he talks about something like this and says, you should try to compute cohomology valued in some perverse sheaf that's imposing the complex moment map condition. And then he very quickly says, well, is probably equivalent to something much nicer. And he describes the much nicer thing, and that's what's led to the BFN construction of the Coulomb branch, which implicitly has a conjecture that the BFN definition is related to something more like this that actually has to do with symplectic vortices that, again, I don't think has been worked out. That actually, thanks. So that actually explains maybe why people haven't looked into it more carefully, because even in finite, like even if you get this as a vector space, you still need a product. So what did BFN actually do? They think of this whole thing as some derived cotangent bundle and sort of map onto the base. Y gets ignored. The complex moment map condition drops out. And so they just look at X valued in V. On the bottom, a gauge transformation everywhere except the origin that relates to the bottom and the top, quotiented out by isomorphisms on the bottom and the top. So this is the space that's called RGV or RGN in BFN. And moreover, there's a natural product on this. Many slides ago, when I was writing like 15 different things that a 3D TQFT does for you, I mentioned Z of S2 is an algebra, and the algebra comes from a 3D pair of pants, the algebra structure. So in this sort of partially holomorphic setting with ravioli, a 3D pair of pants is a super raviolo. It's two little ravioli inside one big raviolo, and that means convolution product on cohomology of spaces like this, and which is what BFN actually showed existed. So they defined a convolution product that gives this space the structure of an algebra. Should also say as an aside, there's these algebras Z of S2 that show up in gauge theories all have quantizations, and quantization comes in physics from, it's called the omega background, and here it comes from turning on equivariance with respect to the action of loop rotation on these disks. So when a priori the convolution product gives you a commutative algebra, so this functions on the Coulomb branch. This thing is a commutative algebra, but it has a canonical non-commutative deformation in this setup, which is where a lot of the interesting representation theory comes in. And so I realize this all, hoping many of you are familiar with this construction by now, but just in case, these weird convolution algebras that pop out are not that horrible. They end up being functions on a finite dimensional variety, the Coulomb branch, finite dimensional affine variety, that is non-compact. So functions are infinite dimensional, but it's not that bad. Let me just give you some of the simplest examples. So if you just plug in C star for the complexified group with zero representation, and go through this construction, you end up with the affine Grassmannian for C star, and at the end of the day, find that this convolution algebra just looks like functions on C times C star. You start to throw in a one-dimensional representation of C star with weight 1, then you get functions on C times C, or T star C as a hyperkähler space. And for general reductive group, and I forgot a Langland's dual here. So for general reductive group and zero representation, it was a theorem of Bezukovnikov, Finkelberg, and Mirkovich, that this crazy convolution algebra is functions on a really nice symplectic quotient, actually, of the Langland's dual by nilpotent subgroups on both sides. Also, in the case of TSU2, this is the Atiyah-Hitchin manifold. These end up being sort of familiar and often very famous and well-studied hyperkähler spaces. Okay, great. So I am now back to doing fine with time. I'll finish soon. So that was Z of S2, and getting back to my 3D TQFT statement, what 3D TQFT gives you is an expected action of this BFN algebra, where it's quantization, functions on the Coulomb branch on any space assigned to a surface. And mathematically, maybe you're now telling me, well, that's not surprising because everything comes from convolution, and that's true. but the results are interesting. The sorts of things that pop out. Playing this act with Z of S2 game on the base pointed maps from P1 into the symplectic target produces, depending on the choice of base points, different Lagrangians in the Coulomb branch. So one gets a module for functions on the Coulomb branch, which ends up being supported on a Lagrangian. And they're very special Lagrangians. They end up being certain flow cycles for Hamiltonian isometries. And they quantize, they're versions of stable envelopes. And they quantize, turning on this loop rotation equivariance, they quantize to Verma modules for quantum Coulomb branch algebras, which are things like finite W algebras and Yangians and enveloping algebras of reductive Lie algebras, very like sort of things that are studied all the time in representation theory. And this is a thing we talked about in a paper from some years ago, and that so we talked about it here. And in doing so, we didn't use the BFN construction of the Coulomb branch because that doesn't play very well. The BFN construction that kills the perverse sheaf and only uses X and not Y doesn't entirely play well with a space of symplectic vortices. So we used a slightly different construction of the Coulomb branch algebra. And that was recently put on rigorous footing by Zhao just last year. So the thing that's happening at infinity is a boundary condition, and boundary conditions, topological boundary conditions will always give you Lagrangians inside the moduli space, and that's I guess that's morally why it's showing up. It's the flow like. There's a stability parameter turned on. It's an Fi parameter that corresponds to an action on the Coulomb branch. It's a C star action on the Coulomb branch, and this is a stable cycle for that C star action starting at a certain point on the Coulomb branch. You can just take spec of this is what happens when you have a module for a commutative algebra. Right, the algebra that's acting is a commutative algebra. It satisfies the elements of that algebra satisfies some relations. Say acting on if here it ends up being generated by a single thing, and acting on that generator, they satisfy some relations, and those relations cut out equations in the Coulomb branch. Yes, this has in our work and combined with Zhu's work, this constructs Verma modules for Coulomb branch algebras. The analogous case of actions on smooth surfaces, I think, is relatively unstudied. Again, defining this requires not quite the BFN construction of the Coulomb branch, though it's the same algebra that should be acting. One thing to say about expectations here is that there's also a mapping class group action that acts on spaces associated to a surface. These spaces are infinite dimensional generally. The action of Z of S2 should commute with the mapping class group action. And there are various reasons to believe that as a module over Z of S2, these state spaces associated to surfaces are finitely generated. And if one wants to understand the mapping class group action, what you really need to do is like sort of understand the generators of this thing of this infinite dimensional space as a module over the Coulomb branch algebra, and then just figure out how the mapping class group acts on the finite generators. I hope that I or someone else can say more about this in the coming years. That would be something cool to figure out. And sorry, let me finish up. To preface another topic that's going to show up in this conference in Konstantin Taleman's lectures, there are lots of connections between all of this and two-dimensional A models. And the picture is that 2D A models live on boundaries of 3D A models. So I have in my head that local operators in a 3D theory act on local operators on a boundary. The TQFT version of that is that given a boundary, there is a sort of half ball cobordism, a half pair of 3D pants that gives an action of Z of S2 on Z of a disk with some boundary condition at the boundary of that disk. And there are many different boundary conditions for a given 3D theory, and they all have to do with two-dimensional A models. To give an explicit example that I think is going to come up in Konstantin's talk as well, putting pure gauge theory in the 3D bulk with, so any G with trivial V, one can define a boundary condition that's labeled by a vector space with a G action. And then what this construction spits out is an action of the bulk Coulomb branch for pure gauge theory on the quantization of a space of maps from a disk to the target with appropriate boundary conditions. And what that space ends up being is loops into W. So the boundary of this disk, which is a loop, is sitting inside W on the boundary. And so one gets part of this moduli space is just loops into W. And because the disk fills in the bulk labeled by G, one quotients out by an arc space by sort of Taylor series loops in G. And that's one way to say, when this is a vector space, that's and adding a bit of stability, that's one way to say quantum cohomology, G equivariant quantum cohomology of W. So what one gets from this picture, which has now been made rigorous, so this sort of picture was discussed in work of Telemann and some work of ours, and was made rigorous recently by Gonzalez Mach and Palmeriano. Anyway, so what I've said it already, one gets actions of 3D Coulomb branch algebras on quantum cohomology.
We are running.
I'm sorry. Yes.
Out of time, but we have been asking questions, so we have
This is the end. This is it.
I see.
Thank you.
Okay, so let's thank Tudor. So we are right. Yeah, we are almost past 10 minutes. So any quick question? Still, we have been interacting with Tudor all along. So yeah, if not, let's thank Tudor again.